All right, I'm going to go ahead and go over the homework from 2.3, starting with number 1. For exercises 1 through 6, draw the next figure and complete a table finding the nth term. Find the 35th term. And so we have lines passing through the same point are concurrent. Into how many regions do 35 lines divide the plane? Well, let's see here. One line divides it into two planes, or two regions, and then two lines divides it into 1, 2, 3, 4 regions. And three lines divides it into 1, 2, 3, 4, 5, 6 regions. So I'm seeing a pattern. So the next would be 8 and then 10. Can I make a generalization or a conjecture? Yeah. Looks like the number of regions is twice the number of lines. So 2n. So if there are 35 lines, there would be 70 regions. Number 4. What's the total number of diagonals in a 35-sided polygon? Well, if you look at here, there are 3 sides and no diagonals. And then 4 sides, 2 diagonals, 5 sides, 5 diagonals. I can see here that every single vertex. This has 1 coming out, 1, 1, 1, and then 2 coming out. Oh, look at that. So it's kind of like if you have n, like in the investigation we had n minus 1 over 2, right? That was the handshake problem. This one will look very similar to it, but it's going to be the number of vertices times the number of vertices minus 3, right? And a y minus 3, because if you look at this, like if there are 3 vertices, none are coming out. There are 4 vertices. Every single vertex has 1 diagonal coming out. There are 5. Everything has 2 diagonals coming out from each vertex. So I'll go ahead and say that again. If you have 4 sides or 4 vertices, 1, 2, 3, 4, then every vertex has 1 diagonal coming out. For 3, it has none. And for 5, it has 2. Right, but if we do n minus 3, what we're going to end up doing is what's called double counting. Because from this vertex has 1, and this vertex has 1, or this vertex has 1, and this vertex has 1. So in order to avoid double counting, I have to divide by 2. Divide by 2. So the final result is this. Let's see if that works. So let's see here. 3 was 0. 4 had 2 diagonals. 5 had 5 diagonals. So if I take, let's do 4. 4 minus 3 over 2 is 4 times 1 over 2, which is 2. Check. That works. It looks like we're good. Then number 5. If you place 35 points on a piece of paper so that no 3 points are in a line, how many segments are necessary to connect each point to the others? Right? So here's the first term Here's the first term, second, third, and fourth. So this has no line segments, 1 line segment, 3 line segments, and 6 line segments. Oh, look at this. This looks very similar to the handshake problem. So again, I have the number of points times the number of points minus 1 divided by 2. And that's going to be it, right? So let's see if that works. So number of points here is 1. 1 minus 1 divided by 2 1 times 0 over 2, which is 0, so that works. Then the second one is 2. 2 minus 1, 2. 2 times 1 over 2, which is 1, and that works. So yeah, looks like it works. Why does that equation work? Well, if you look at this, in this one, you have one line, right? So that's going to be 2 points. Each has one line coming out from it. Divide by 2 to not double count. This one, there are 3 points. Each point has 2 lines coming out. Divide by 2, so you don't double count. This has 4 points. Each point has 3 coming out. Divide by 2, so you don't double count, right? And it's similar to 4, if you look at that, where here, you're going to visualize this, that this has 3 points, 0 lines coming out. Divide by 2, so you don't double count. 4 points, each point has 1 line coming out, 1 diagonal. Divide by 2, so you don't double count. 5 points, each has 2 coming out. Divide by 2, so you don't double count. So you can see it's like 3 to 0, 4 to 1, 5 to 2, a difference of 3. Whereas here, 2 to 1, 3 to 2, 4 to 3, a difference of 1. So that's number 5. Number 6. If you draw 35 lines on a piece of paper so that no 2 lines are parallel to each other and no 3 lines are concurrent, how many times will they intersect, right? So again, it says that no 3 lines are concurrent. What does that mean? That means that if I have 3 lines, they're not all going to intersect at the same point, right? So these are concurrent lines, so that's not going to ever happen. And let's see what it says. How many times do they intersect? Well, this is 1, 2, 3. They intersect. They never intersect here. They intersect once. They intersect 3 times. And then the 4th time, 4 lines. So no 2 lines are parallel to each other. And they're all going to intersect at least once. And I think actually, yeah, these are going to intersect over here eventually. So I'm going to redraw this. Hold on. Okay. So let's see. 1, 2, 3, 4. Okay. So that's going to be 1, 2, 3, 4, 5, 6. So the 4th one is 6. Okay. So, oh, look at that. 0, 1, 3, 6. 0, 1, 3, 6. See that same thing again, where I have 1 never intersects. Divide by 2. 2 intersect once and divide by 2, so you don't double count. Here I have 3. Each line intersects twice. Divide by 2, so you don't double count. I have 4 lines here. Each line intersects 3 times, right? Like, 1, 2, 3, and then divide by 2, so it don't double count. So we see it's the number of lines times 1 less than that, divide by 2, so we don't double count. Number 7. Look at the formulas you found in exercises 4 through 6. Describe how the formulas are related, then explain how the 3 problems are related geometrically. Okay, so it's basically saying the formulas in 4 through 6 are n minus 3 over 2, n minus 1 over 2, n minus 1 over 2. Explain how the 3 problems are related geometrically. And let's see here. I'll show you. Yep. So you can see they're visualizing the points in exercises 4 through 5 as vertices of a polygon. as an exercise 4, the total number of segments n, random points is the number of diagonals the inside polygon, plus the number of sides. Thus, the total number of segments connecting n random points is this. So I think what they're getting at is when you had number 4, you're not including the sides, so your equation's changing. Whereas here you're including the diagonals and the sides. And it looks like they said that when you have n minus 3 over 2, when we add it to the number of sides, what do we get? Well, in order to add fractions, I have to keep the denominators the same. And so we go n minus 3 over 2 plus 2n over 2, which is equal to n minus 3 plus 2n all over 2. And that's going to be equal to n squared minus 3n plus 2n all over 2, which is n squared minus n all over 2. And so now I can see if I factor out the n, I'm going to get n minus 1 over 2, which is what you had before. So that's how they're related algebraically to each other. And geometrically, you can see it's based on the picture, really, where here you have a polygon with all the diagonals and all the sides, and you see this pattern. And here it's just the diagonals, and you see that pattern. 7 and then 9. Each person at a party shook hands with everyone else exactly once. There were 66 handshakes. How many people were at the party? Well, the formula is n minus 1 over 2. And you could solve this algebraically or just kind of guess and check that we know. Let's pick a number like 10. 10 times 9 over 2. That's 90 over 2, which is 45. That's too small. Let's try 11. 11 times 11 minus 1 over 2. 11 times 10 over 2. That's going to be equal to 55. Still too small, so it's probably going to be 12. 12 times 11 divided by 2. 12 times 11 is 132. Divided by 2 is 66. There we go. So the answer is 12. All right. That's the homework for 2.3.